Perfect. So welcome everybody to the August OpenXLA monthly community meeting. This is a 30-minute meeting for this particular month. We have it divided into two different parts. The first part is going to be focused on a co-presentation between Google and ARM. So I'm going to turn it over to Sandeep very shortly to introduce everyone. And then we'll spend some time with Kevin Gleason to talk about some of the stable HLO updates as well. And then the other thing that I wanted to point out is that we will have a presence at the PyTorch conference. So if anybody is going to be in San Francisco or is going to be attending or lives in San Francisco or in the Bay Area, please do come to the event that we'll have afterwards as well. Did someone raise their hand? Okay, awesome. Perfect. All right, with that, I'm going to turn it over and I'll send out emails with all the details and there will be swag. So if you want to get some OpenXLA t-shirts, if you didn't get any during DevLab or you want to get some extra ones, definitely come because there will be a swag giveaway. All right, with that, I'm going to turn it over to Sandeep and Ty to talk about stable HLO.
Thanks, Aditi. So yeah, my name is Sandeep Dasgupta. I am a member of Stable HLO team at Google. And it's truly a pleasure to be here today sharing the spotlight with our esteemed colleagues from ARM. We are excited to co-present the results of a significant milestone in our collaboration, which is to align the stable HLO and TOSA quantization semantics. Let me first introduce Ty Lee, a key developer from ARM who has been instrumental in this joint effort. We would also like to extend a special thanks to Eric Kunze and Dominic Sims, the author of the RFC that kind of underpins much of our work. Their feedback and technical guidance were invaluable in navigating the complexities of the project and achieving the milestone that we'll be presenting here today. So let's get started. Yeah, the previous slide, please. Yeah, so to give you a roadmap of today's talk, we will start with some background on stable HLO and TOSA quantization primitives. Then we'll shed some details on the RFC in particular to align the quantization semantics of stable HLO and TOSA. And also the hurdles we faced in aligning their frameworks. And finally, we'll go into the proposal that we have been working on. Next slide, please. Let's focus a bit on the TOSA IR. TOSA IR, in essence, is a collection of tensor operations commonly found in deep neural networks. It is designed with flexibility in mind, aiming to run efficiently on a variety of processors. Crucially, it requires bit accurate definitions of its integer operations, ensuring consistency across diverse hardware. And there is also an upstream dialect that most of us are aware of that directly mirrors the TOSA specification. Next slide, please. Yeah, here we'll illustrate how quantization is expressed in both stable HLO and TOSA IR. Let's take a quantized add operation as an example. In stable HLO, we use the uniform quantized type, which is borrowed from the upstream quant dialect. The quantized type, uniform quantized type, has floating point scales and integer 0 points, and these are called quantization parameters, which are used to map between quantized integer values and floating point values. The example at the top shows a stable HLO quantized add operation with floating point scales like 0.025 and so on, and 0 points as -1 and so on. One of the interpretation of such a program, such a stable HLO quantized program, could be to dequantize the operands of add to floating point values, do the floating point addition, and finally quantize the result back. Below, we have the corresponding TOSA implementation of similar quantized add using rescale operations. Here I would like to note that TOSA operations don't accept tensors with uniform quantized types. Quantization has been moved to explicit rescale operations. Rescale operator uses multiplier shift, which are both in integer constants. So in this example, the TOSA IR example, we have two rescale operations, one for each operand, then an integer add followed by the final rescale of the result of that. Please note that the entire computation is happening with integer arithmetic. Yeah, next slide, please. Now let's connect the dot between the TOSA rescale parameters, which is the multiplier and the shift, and the floating point scale that we use in the uniform quantized types. Let's first look at the semantics of the TOSA rescale operation, which has operands as input and some constant attributes as multiplier, shift, 0 points, and input 0 and output 0, which is conceptually doing something as written in this expression. The formula here uh, has a close resemblance with the expression of uniform quantization, which makes the relation between the rescale parameters, multiplier and shift, pretty clear. And for below, we can see the relations. The scale, the floating point scale in uniform quantized type can be conceptually characterized as multiplier into 2 to the power minus shift. So this is just a conceptual thing. The exact relation is can be a bit intricate, but this is can be simplified like this. Next slide, please. Now let's talk about the goals of this collaboration. Our primary aim is to align the quantization semantics between TOSA and StableHLO. This alignment will facilitate a seamless conversion of quantized StableHLO programs into TOSA by utilizing the TOSA rescale operations. Additionally, we want to leverage the StableHLO reference interpreter to validate this alignment. So the results of the StableHLO reference interpreter can be compared against the results of TOSA compatible accelerators, ARM accelerators, and once this alignment is achieved, then we can say that okay, this conversion, this alignment conversion is validated. And at the StableHLO and the interpretation of the StableHLO, quantized StableHLO using the StableHLO interpreter can be achieved by emulating the TOSA rescale semantics. And in some of the following slides, we'll see how that emulation will happen. Now, by achieving these goals, we aim to enhance the interoperability between StableHLO and TOSA. Next slide, please. Here I show the conversion between just conceptual diagram of converting a quantized StableHLO program to a quantized TOSA program. This conversion presents various challenges. For example, the rescaling an operation and deriving the corresponding rescale parameters from the floating point scales depend on both the operation and the data type. The process can be intricate and requires careful consideration. Fortunately, our ARM developers possess in-depth knowledge of these formulas, which enable us to navigate these complexities pretty effectively. Next slide, please. So here I'll be exemplifying a few challenges that we can foresee. Let's make the challenges a bit concrete with TensorFlow light multiply operation. Like StableHLO, TensorFlow also uses uniform quantized type. Hence, it can be thought as a close proxy to StableHLO quantized operations. So at the top, we can see a TF light multiply operation, and at the bottom, we have the corresponding TOSA IR. And here we will mostly focus on I think one of the we will mostly focus on the how the multiplier of the rescale operations are derived using the floating point scale values. So in the TOSA IR, we can see that for the first two multiplier operations, scale value of 1 is used, and for the last multiplier, we can see the rescale value of this expression is used. This makes sense for multiplier operations, but let's see how it changes when we change the operation. Next slide, please. So this is the add operation, and similarly, we have the TOSA implementation for this StableHLO quantized add operation. So here, to derive the multiplier, we have this expression for the first rescale operation. Next slide. And there's a similar expression is used for the second rescale operation. And next slide, please. And this is the expression we used for the rescaling of the final result value. A key thing to note here is that this derived multiplier depends on the data type of the quantized output type. So these are the few challenges. To summarize, the challenges are the derivation of the multiplier needs a little bit of consideration because it can depend on the operation, at the same time the data type of the quantized output type as well. And this is just for multiply and add. For other operations, the derivations could be similarly involving. So next slide, please. So to address these challenges, we propose a two-phase approach for converting from stable HLO to TOSA. In the first phase, we convert quantized stable HLO program to a mix of stable HLO and TOSA with rescale operations. I would like to note here that the output of phase one is key intermediate stage, which can be converted using phase two to an IR serving two key goals of our collaboration. So, for example, the phase one output can be converted to a pure TOSA program using phase 2A. Uh, this serves the goal of aligning the quantization semantics between stable HLO and TOSA. Alternatively, the phase 1 output can be converted to a pure stable HLO program using phase 2B, which can be interpreted using stable HLO interpreter. This serves our second goal of cross-validating the alignment using stable HLO interpreter and comparable TOSA implementation backends. Now, in the next slide, I will go into the details of these phases. So, next slide, please. So this is about the first phase of the proposal. Here, the intention is to convert the quantized stable HLO program to a mix of stable HLO and TOSA operation. The TOSA operations will be the rescale operations only, no other operations. So, so we introduced this MLR optimization switch, which is stable HLO quant legalized to TOSA rescale. What it will do is that it will take this quantized stable HLO program and it will convert it into this TOSA implementation, where, for example, in the this is the add program here. The operands of the add are piecewise rescaled, and then the integer add stable HLO add happened, and the result of the add is rescaled again. Now, as discussed earlier, this phase is pretty challenging since the rescale value calculations have some TOSA specific details. Thanks again for the ARM developers who helped in implementing this phase. Next slide, please. So here, this is, as I said, that the output of the phase one is critical, and from there, there can be different pathways serving different goals. So one of the pathway is that we can convert this intermediate output of phase one to a to a pure TOSA program, and this will and this is the full conversion from the stable HLO quantized program to the TOSA program. Next slide, please. Yeah, alternatively, what we can do is we can take the output of the phase one, and the output of the phase one has rescale operations. So we can use a switch TOSA rescale legalized to stable HLO. As the name suggests, it will decompose the rescale operations, TOSA rescale operations, into primitive stable HLO operations involving add, multiply, and etc. And with that, we'll get a pure stable HLO program, which is interpretable. And at the end, I have shown the command line command line switches to actually interpret the program, and we'll see in a while that some of this is already working. So next slide, please. So where do we stand with this implementation? Well, in the stable HLO specification, we explicitly called out that the stable HLO quantized types can be interpreted flexibly, either using floating point semantics using uniform quantized type, or as full integer semantics using rescale operation. The choice is exclusively determined by the specific implementation. This helps us bridge the gap between the quantized semantics of the two frameworks. Phase one of the proposal is under active implementation. Currently, we cover only add and sub operations, and we plan to support more involving ops in the next batch. Also, the current support is limited to cases when all the operands and results are quantized and when certain parameters of rescale operations has some specific values, as noted in this slide. In future, we plan for kind of feature completeness. Finally, the phase 2B is also implemented thanks to ARM developers again. Next slide, please. Now, to wrap up, the key takeaway is that our proposal empowers us to kind of convert quantized stable HLO to TOSA while preserving the semantics. This means that we can interpret stable HLO quantized programs with semantics that perfectly mirror their equivalent TOSA counterparts. Additionally, the approach used to convert a TOSA rescale operation into stable HLO primitive operation demonstrates how support for dialects other than stable HLO can be added to the stable HLO interpreter. This strategy is likely to be useful in future use cases that have similar requirements, allowing them to benefit from this approach. And with that, thank you for your time. And yeah, I'm happy to take questions at this point.
Great. Thank you so much. Great job to the team. So one thing is, let's open up the floor for questions, especially if you've got questions for Ty. I think he's more than happy to answer them. So we have about 3 to 4 minutes for questions. I'll just give it like a few 30 more seconds to see if there's any questions. If not, we'll keep moving.
Maybe I'll just dip in real quick and say thank you to Sandeep and Ty. Ty did all the work, and Sandeep was very helpful from the ARM perspective. Excuse me. It's good to work with you guys.
Thank you, Eric.
Thank you, Eric. Okay, all right, so if there's no questions, let's keep moving. I'm going to turn it over to Kevin to give you some community updates for Stable HLO.
Sounds good. Thank you. You can go next slide. So I'm realizing I should have linked pretty much all of these items, and so I'll be sure to update this with direct links to each individual bullet here before we send the slides out. But yeah, I just wanted to cover a few things that were landed that are more on the stable HLO or MLAR side, or things that we've helped out with in addition to the ARM stuff that Sandeep just shared. So yeah, recently landed, there were a few new ops in stable HLO, TANOP, custom call op with a dictionary for backend config, basically a XLA FFI dictionary, and then variadic all reduce, all gather, variadic collective operations. In general, the criteria of a new op is that both the framework and the hardware want it, and we were seeing many uses of custom calls or unregistered attributes popping up for satisfying these 3 op use cases. And so now we have them all added, and I think that should be, it puts us in a very good place, puts us in high parity with public framework features, as well as sort of the public interface of XLA that's currently desired. Another one is int2, new data types in stable HLO. There was a request put out for int2 types, and that one has been approved and implemented. That includes using int2 in quantized types as the storage type. And then next up is .general algorithms. This was a pretty cool one that we are mostly landed. It's in stable HLO. We're still piping it through all the way to HLO, but the RFC was proposed and approved. Basically, there's a common issue that different hardware uses different default algorithms for calculating dot. And that means that when you take your program and switch which hardware you're running it on, you can see different results. And a lot of it just comes down to this different dot algorithm that's used. So this is a means of explicitly specifying what dot algorithm you want to use for those calculations. And I think there's already pretty broad support on various algorithms for GPU in XLA. I'll link a full list of what exists today. And it's super flexible to specify new algorithms. So anything that works for in your hardware, we can add it as well. Next up is Intel's XLA CPU quantization RFC. We heard from them at the last community meeting, and that has since been approved, and PRs will start to be landed there. The main thing to keep out for in terms of, or to keep an eye on there in terms of community, is that they'll be enhancing the quantization pattern matching. So if you have a hardware backend that has support for various quantization schemas, there's a high opportunity to share these new and enhanced quantization pattern matching once they come about. And next is composite ops. A while ago, we had added these to stable HLO, and then the on-device machine learning team at Google actually used composites successfully to accelerate various models for like capturing a higher level abstraction that's supported on their hardware and piping it all the way through. So we have a good proof of concept already in place, and now we have plumbed this all the way through to HLO. So from framework to hardware, there is support for composite operations for capturing higher level abstractions. One major use case for this is just to ease pattern matching for things like to ease pattern matching for hardware supported abstractions. Next is future RFCs. I think there was just a message in chat from Alexander. Yeah, this is AWS Trainium has support for some floating point 8 types that are not yet supported in stable HLO. So we're looking to get this one approved and implemented probably by the end of this week. I think that we're in the middle of the 2-week RFC period for this right now. So if you have any thoughts or comments on that, feel free to leave them on the pull request I linked there. And then lastly, I want to cover a few things that we're looking into now. These are things that you can expect future RFCs on, but if these are topics that are of interest to you, feel free to collaborate with us, reach out to me early, just to get in on the early design stages as opposed to later down during the RFC period. But yeah, we're looking into ragged tensors as well as subchannel and superblock quantized data types. This would be like enhancing the actual MLIR uniform quantized type sorts of things. Looking into getting an RFC on that out in the near future. And then the last two things we're looking into are componentizing HLO, starting with basically HLO is a bit of a mess when it comes to certain components. There was a client service model that seems to be a bit archaic at this point. And so we're looking into making it reflect better, like the LLVM product directory structure, for example, just more clean separation of what's IR, what's pass infrastructure, what's pass definitions, not adding anything new, just moving things around so it's super clear what's hardware independent, what's hardware specific, and it makes it easier to plug and play. And then last one is we're considering the future of MHLO a bit more seriously now. Pretty much every day we see increasing requests for optimization passes in stable HLO for users who depend on stable HLO but not the XLA repo. And so we add those to the stable HLO repo, and what we see is that stable HLO and MHLO are becoming more and more similar by the day, and this really just leads to an extra layer of tech debt. So we are no active proposal yet, but we are highly considering what to do with MHLO and if this layer of tech debt is actually worth it, and probably see an RFC on that in the coming weeks. And that's it.
Awesome. Let's pause to see if there's any questions. Awesome progress. All right. If there's no questions, then just a quick reminder, there will be an OpenXLA booth at the PyTorch conference, so please do stop by and see us. We will have swag. There will be a swag giveaway, and then we'll also have a happy hour. I'll send out information about details on that as well, and there'll be a swag giveaway at the happy hour too. So hope to see you soon in person. If there's no other questions or comments, right, we'll see you all, hopefully at the PyTorch conference, if not, at the September meeting. Thank you so much, everybody.
Thanks.